Hi everyone, we are back and we are going to do our Pset solutions. Let's just make sure that you can scroll up to the top. Oh, here we go. Now we're starting to read it in. Excellent. So we're looking at a system of nickel and tantalum. So let's go ahead and first fill out the phase diagram. So this is pure nickel, this is pure tantalum. So this will be nickel tantalum plus tantalum. This will be tantalum plus liquid. This will be liquid plus nickel tantalum. NiTA2, NiTA plus this. This will be Ni2Ta plus this. This will be this plus this. This will be liquid plus Ni tantalum. This will be liquid plus beta, everything here. This will be alpha plus this. This will be this plus this. This will be this phase plus this. This will be this phase plus alpha. This will be nickel plus nickel. This will be nickel plus this. And this will be obviously liquid plus nickel tantalum. So obviously I'm expecting you to label those, do that a little bit nicer. But again, you kind of see the picture. If you want to look at a phase, see what's touching on the left side, you could just draw basically an isotherm, constant temperature. So what's touching here for the phase in these blank regions. Fantastic. So those are the phases. Let's look at, let's do congruent melting points first. We can make sure that we're good to go here. So congruent melting point here, congruent melting point here, because pure material, so remember, it goes from pure solid to pure liquid. There's a congruent melting point here. Oops, let me erase that. I need to build in the functionality where I can just kind of click and I need to get this out of the way too. Sorry, I'm just moving this guy, my timer out of here. Let's erase. So let's go back. So this would be a congruent melting point. This is not necessarily a congruent melting point here. And that is all there is. Fantastic. So let's go and let's erase here. Now let's go for our congruent melting points. So we are going to indicate, so again, we want to see if this is bunny ears, that's going to be a U. So I'm going to say red is going to be my eutectic. So let's look for eutectic points first. So I can see eutectic here. I can also see, is there any other eutectic? There's kind of going to be a little eutectic here potentially. Liquid to, basically a two-phase solid. So like this is like alpha plus beta. So possibly here, but I wouldn't really necessarily expect you to get that one. So there it is. That's it. So let's go ahead and erase. So that would be the eutectics. I'm going to pick another one. I'm going to now do let's do the same feature, eutectoid. So now it's not liquid, it's going to be single phase solid, nickel tantalum to two phase solid here, this plus this, two new phases. So that would be a eutectoid. Beta here to alpha plus this. I would say this could be a eutectoid, and then that would be it. So this is not eutectic because I'm just still NiTA2. So nothing is unique really there. And the same thing on this side as well. Fantastic. All right. So what about a peri? So let's do a peri. So a peri, I'm going to look at something like this or something that looks like this. So I need, this is going to be a peritectic. And remember, that's alpha plus liquid to beta. So this would be a peritectic right here. What else? Alpha plus liquid, two-phaser. I'm just looking over here. This would be this plus liquid to here. This would be a peritectic. We see here, this is also going to be a peritectic right in there. There we go. And actually, if we zoom in, let's see here. That is going to be There's probably a little region here where this is probably like a two-phaser that goes like in a two-phase region here. But this is also going from nickel. So this would actually be, what was our symbol for? Actually, eutectic here. I'll switch to green. So I just see quickly. Let me get over here, move that. So if we look right here, we have this green. Nickel goes to this two-phase solid region here. And again, there's probably a little distinction here in this phase where it could be, actually probably could be an allotropic phase transition. But anyways, beyond the scope of what I'm expecting to have you all demonstrate in this course. So I think those are all the peritectics that we have in this system. I'm just looking and scanning and trying to see if we've got any other ones, but that's pretty much it. Now, we could also look for a peritectoid. So something where we're looking from basically a two-phase solid, so like an alpha plus beta, to a gamma. So actually, let's go ahead and let's change our color one more time. Let's change it to, let's grab some more colors. I'm going to do purple here. So do we have any, basically, a two-phase solid to a single phase? So let's look for those features and structures again. Two-phase solid to another solid here. I'm not seeing any. Let's see, can you all see anything? Or we're going from solid plus solid to another new solid. Let's see if we're looking at it here. Not to a brand new solid. We were saying that this is probably a eutectoid. So solid plus solid straight to a new one. No, I don't see any. The only thing that could be happening would be again over here. It's like solid plus this solid to this solid, but again, that's very, very close. So you can estimate something, but I think we're good to go there. Fantastic. All right, so let's go ahead and let's continue. Composition of 0.95 mole fraction of TA, 0.95 mole fraction or atomic, basically, 0.95 atomic percent, 0.95 of TA at 500 degrees C. So we're looking at something over here, 0.95 right here. Excellent. So we're looking at 500 C. What are the phases that exist in this region? So in this phase, we are TA plus NiTA2. So we're in two phases. So degrees of freedom plus phases equals components plus 2. Actually, plus 1, excuse me. So let's go ahead and draw. Let's erase components plus. Here we go. Plus 1. So components is 2, so this is 3. Phases 2, so our degrees of freedom here is 1. So we're going to have a composition that's in the TA phase, which will just be equal if we draw this line at approximately 500. So something probably on this. It's a very bad straight line, but you get the picture. So 4.95 here. So basically that's going to be around 100. So for that composition, or 1.0, you could have a composition that's NiTA2, and that's going to be equal to about, let's just call this 68, 67, something of that nature. So those would be my compositions in that phase. That's my degrees of freedom. And if I want the fraction that's in the tantalum, that's going to be equal to 100 minus 68. And then I'm going to go to opposite. So I'm actually going to go 95 minus 68. And then the fraction that is going to be the tantalum, fraction that's going to be in the NiTA2 is going to be equal to 100 minus 68. And then it is going to be the opposite. So I'm actually going to go 100 minus 95, which makes sense. Again, the fraction of NiTA is much lower because I'm closer to the tantalum side. Fantastic. What else? Relate the chemical potentials of each phase in this region. What are the degrees of freedom? Degrees of freedom we already answered. We got the phases. We got the composition and fraction. Chemical potentials. So if we are in a two-phase region, the chemical potentials of those two phases must be in equilibrium. So chemical potential of tantalum phase and the NiTA2 must be equal here. So, excellent. We got that problem done. So now let's draw the free energy curves for the phase at 1750 degrees C. What is a common tangent? So 1750. So let's go ahead. Let's just say, let's see, what are these tick marks? Let's delve into these tick marks here. We can see what we're dealing with approximately. So we can say, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5 right here. So we'll draw our phases basically all the way across here. So if we were to draw our free energy curves for this, for basically this scenario, let's go ahead and first let's erase everything that we've kind of written up here. Let's erase it over here. So when you're drawing these free energy curves, we want to keep in mind, actually be very aware. Actually, I'm going to delete this here. Delete everything I want to delete, but okay, good. So I am going to set up my curve like this. So this is my free energy versus basically the mole fraction of, tantalum. I just do B. You can do tantalum here. So from here to here, I am pure liquid phase. So I'm only in my liquid phase, and actually I'm going to redo that right now. Liquid is going to be blue. So I am pure liquid phase here. Between that composition, and I should have drawn this as black. So let's actually do that. Between this composition and this composition, what phases am I in? So here and here, I'm actually liquid, and I'm going to change here. I'm going to be liquid plus, I'm going to just name this green, plus a second phase, which is NiTA2. So that will be this phase right here. Now, between here and here, I'm just pure, right here, I'm just pure NiTA2. So there's no two-phase region in this little tiny section. But between here and here, I'm going to draw another curve. I'm not going to do blue, but I'm going to do gray. Between here and here, I am a two-phase region, and I'm going to be basically my NiTA2. So let's zoom in. In this phase, I'm going to be NiTA2 plus my gray, which is going to be my tantalum. So I'm in a two-phase region here, and then finally, from here to the end, I'm just pure tantalum. So what does this mean? When I'm between here and here, I need to have a common tangent. So I'm going to draw my common tangent as a different color. All my common tangents are going to be orange. Actually, I don't like orange. I don't like orange. I used to love orange, but for personal reasons, I really don't like orange anymore. Let's go ahead and let's make it kind of this hot pink color, make it stand out. So I'm going to have a common tangent where here, in between this two-phase region, the slope must be equal because the chemical potentials are equal. That's the whole concept. My chemical potential is equal to the dG roughly. Not exactly, but dG dxB. So if I'm in a two-phase region, my chemical potentials are equal, therefore my slopes are also equal. So when I'm drawing this region where like liquid is pure phase and then it's a two-phase and then there's no more like liquid phase that's appearing, it's going to come in, and this is always how you want to draw these. I'm the lowest phase region here. It comes in, it touches this. That's my slope at this point, and then it just disappears. My TI, and like when you look at excuse me, we can look at another concept or another idea here. So let's look at this other two-phase region. So now we're in a two-phase region where I have NiTA and then tantalum. Same thing. We don't care. It doesn't necessarily, the slopes have to be exactly the same and equal, and they have to kind of touch because you have that gap here. But I just have some slope in this region. So, but the same concept holds. When I'm over here, if I'm looking at my nickel NiTA2, I'm higher here because lowest free energy wins. Liquid is the stable state. It is the equilibrium, thermodynamically lowest energy state. So I'm higher here because lowest energy wins, liquid. Here in this region, I have to touch here. Then I'm lowest. Then I'm going to touch here because I'm in a two-phase region now with tantalum, and then I disappear. And tantalum, again, it's just hanging around here. Doesn't even exist here because I'm pure NiTA2. But here, when I'm in the two-phase region, I touch, and then I'm the lowest energy. And that's it. That's how you draw those free energy curves. So, first problem done. Now let's do one more, and then we'll be done for this problem set. All right, so let's go to our next problem here, and our next example. All right, so we're going to go ahead and fill out. We're looking at aluminum and SM. So let's fill out the phase diagram here. So this plus this. Let me change my color. This phase plus this phase, FCC plus liquid, liquid plus this phase right here, liquid plus this phase right here. Here we're going to have liquid plus this phase, liquid plus this phase as well. And we're going to have here solid phase plus solid phase here, solid phase plus this solid phase here, this solid phase plus this solid phase, this solid phase plus this solid phase, this solid phase plus liquid, liquid plus this BCC right here. We're also going to have this rhombohedral right here, and this is going to be plus BCC here. This will be this solid phase plus BCC right here, this solid phase plus this solid phase. So there we go. Now let's go ahead. Congruent melting points here. Here, we're also going to have a congruent melting point here, and then possibly here, but honestly, this is probably like this plus liquid here, but again, we'll say it's a congruent melting point like this there as well. Now, what about our invariant points? So we went through kind of the features we want to look for last time. So what is this invariant point? This is going to be eutectic, liquid plus the two-phase solid region here. What about this point? This is going to be solid to, basically, this is a solid phase region here, and it goes to, let me see here. Let me actually quickly, we can actually erase, hold on a second here. Actually, let's go ahead and let's draw. So what about this? Liquid to solid plus another solid. So this is going to be a eutectic point right here. That was our congruent melting point. This is a solid phase plus a solid phase. So two-phase solid to a new two-phase solid. This is going to be a peritectic point. So that's a critical aspect as well. Interestingly here, this is a liquid plus this, and this is a pure phase solid to a liquid plus another solid. So again, you could kind of think of that as like somewhat of a peritectic point as well, but that could be an invariant point as well here, although it's not a common one in terms of our processing routes. But it does exist. So this is a solid plus liquid to a new solid, so that is definitely a peritectic. This is definitely a eutectic. This is a solid to two new phase solid regions, so that is a eutectoid. And that is pretty much all we've got. So yeah, this is definitely a peritectic here, although processing-wise, it's not as common. Fantastic. So what is the question actually asking us to do? So boom, we did that. We did this. We need a composition of 0.75 SM at 700 K. So 0.75 at 700 K. So we're looking at something right here. So in this region, we have degrees of freedom plus phases equals components plus 1. So we know we're always components. What are my components? Aluminum and SM, 2 components. So this is 2 here. Phases, 2. What are my phases? So we're going to have some composition that is AlSM2. We're going to have some composition that is, I'll call it rhomb. And then you'll have fractions as well. So the composition of my rhombohedral, let's call it 0.98. Composition of this is 0.5. So now my fraction of rhomb is going to be equal to 0.98 minus 0.5. And then remember, we run to the opposite. So if I'm looking for rhombohedral, I'm going the opposite. So I'm actually going to have 0.75 minus 0.5. And if I'm looking at the fraction that is in the AlSM2, it's going to be that same denominator, 0.8 minus 0.5, but we're also going to, again, run opposite. So it's going to be that 0.98 minus 0.75. So kind of in the middle here, and those values kind of reflect that. Composition, again, the chemical potentials also must be equal, so remember that. And yeah, so chemical potentials must be equal. So chemical potential in my ROM must be equal to my chemical potential of AlSm2, etc. 1500 K. So at 1500, we need to draw my free energy diagram here. So actually, I want to, let's see if we can do this. So at 1500 K, I'm going to delete everything. I don't actually, hopefully this doesn't delete the page. Yep, it did. I knew it. Hopefully this just deletes. There we go. Now I want to, can I cut and snip? Let's see if I'm still figuring out all these tools. Here we go, lasso select. So I want to select this and I want to move it. So Control C. When I do the lasso select tool, how can I, let's see. I'm just trying to figure out how to do some of these tools. So, because really I just want to, here we go, screen clip. Yeah, but I want to stream. Here, what I'm going to do is this. I'm going to do the old-fashioned way. I'm going to just clip like this. I'm a very old dog at this point. You can't show me anything new. Or else I freak out. So let's go ahead and do 1500. Oh, let's go back to my drawing board. Literally back to the drawing board. So I'm going to go 1500. We're going to go across here. So now I am going to start to segment this just like we did last time. So this is going to be, that's horrible, G versus X SM. So we're going to have a dashed line here. We're going to have a dashed line right here. We're going to have a dashed line right here. And we're going to have a dashed line right here. And that's it. Not too bad. So I'm going to simplify this instead of kind of drawing out long form. I'm just going to kind of speak this. So in the first region, I am pure liquid. Then I'm going to be in this region a liquid plus some solid phase AlSm3. So I'm just going to denote that by this solid 1. Now again, I want you to write out this explicitly. Then we'll have a two-phase region here, S1 plus a new solid phase, S2. Then you have S2 that comes back and then is also in equilibrium with my liquid as well. So what we can go ahead and do here, and you're going to see actually in this problem, the liquid's going to have to do something funky. And then finally, we're liquid here. So again, I'm just going to draw arbitrarily my common tangents. And I'm just going to draw it. We're going to do the hot pink again. So I'm going to say this is going to be my common tangent. I'm just going to draw the slope like this, and then we'll call it like, we'll call the slope like this. Yeah, we'll just keep it. I'm just going to draw it like this, because I'm just looking. Yeah, I'm going to undo that. So I'm just going to draw it this. I'm just going to draw it like this. Again, doesn't matter. Again, it's still saying that the slopes are equal, but again, in each of the regions that are in equilibrium. So I'm going to go ahead and I'm going to draw my liquid. So actually, I'm going to draw the solid first. So the first solid is going to be pretty high up here, and then it is going to touch at this edge here. It's going to touch here, and then it's going to be gone. The solid 2 is going to come, and it's going to be not existing, and then it's going to touch here, common tangent in this region, common tangent in the next region, and then it disappears. Now my liquid's going to do something very kind of funky. So it's going to be low here, it's going to touch, it's going to kind of disappear, and it's higher and higher and higher, but then it's going to kind of come back down, and then it'll just kind of hang out here. But that's it. That's all we wrote. So, well, thanks, and we'll see you in the next video, and study hard for your exam. We'll see you then. Thanks. Bye.